In this video, we're going to look at partial derivatives. So consider this function z equals f of xy equal to x squared plus xy plus y squared, whose graph is shown right here. We're going to use this to introduce the idea of a partial derivative and what it means graphically. Okay, so suppose first that we let y equal 1. Notice this y-axis is right here. It's not in the typical direction, but it's made to be easier to see here. So y equals 1 is right here, and that's this plane that is coming through this paraboloid. Okay, if we plug in 1 for y into the function, we get x squared plus x times 1 plus 1 squared, or 1. Now, since y equals 1 is a constant, the graph really only changes along this xz axis, okay, where they're intersecting, in other words. The slice of this 3D graph along the plane y equals 1 is this parabola right here. So that's the line along which the curve, this three-dimensional graph, and this plane intersect, okay? Now that we have just a simple curve, we can talk about derivatives. We can find the derivative of f of x comma 1, that's the derivative of this red parabola, with respect to x, okay? So here is the function f of x comma 1. We're going to differentiate that right here. Its derivative would be 2x plus 1. Okay, so that tells us the slope of the tangent line at any point along here with respect to x along the x-axis. So for example, if x is 1, we plug 1 in right there, we get 2 times 1 plus 1, or 3. In other words, the slope of the tangent line to the parabola when x is 1, that's right here, the slope of that line is 3. Okay, so generally you can compute these derivatives, but we don't always want to plug in numbers for one of the variables because that makes it more specific. We like to keep things general. So instead of actually plugging in a number for y, you can just pretend y is a number and then plug in a number later when you want to find the slope of a tangent line somewhere. Okay, so in general, instead of replacing y with a fixed number, we can treat y as if it were a fixed number or a constant and differentiate f with respect to x. When we do that, we get what is called the partial derivative of f with respect to x. There's two common ways to denote that. Using this notation, you would write it partial of f with respect to x, or using this notation, you might write f and then a little subscript x. Both of those mean the partial derivative of f with respect to x. Or you can do the opposite and treat x as a constant if you're going to find the slope of the tangent line along that y-axis, okay, and differentiate with respect to y. So that would be called the partial derivative of f with respect to y, denoted like that or like this. Okay, so here's another example of a curve, okay. The partial derivative with respect to y means you're holding x as a constant, so you imagine a plane going through your curve that's parallel to this y-axis, and then when you plug in numbers and find the derivative, you're finding slopes of the tangent line along that curve where the plane and this surface intersect. Same thing here in the x direction. Okay, let's practice finding some partial derivatives. So if f of xy equals to x squared plus xy plus y squared, then the partial of f with respect to x. To find that, we treat y as if it were a constant or a number. So if y is a number, then y squared is a number. Okay, and then if y is a number, it's sort of like the coefficient of the x here. So for the derivative of x squared, that's just 2x. Now for the derivative of x times a number, for example, the derivative of 3x is just 3. Okay, so the derivative of x times a number y is that coefficient y. Y is essentially like the coefficient of x. And because y is a number, y squared is a number, so the derivative of that term is 0. And then once you get the partial of f with respect to x, you can plug in numbers for x and y to find the slope of the tangent line at a particular point. So you could plug in 2, 3, 2 for x, 3 for y. Okay, and that would give you 7. So that would mean that in the x direction, okay, so you're treating y as a constant, so if your surface here intersects a plane that is parallel to the x-axis, at the point where they intersect, the slope of the tangent line is 7 at 2, 3. Okay, partial of f with respect to y. For that, we're going to treat x as a constant. So x squared is a constant, so its derivative is 0. The derivative of x times y. For that, if we're treating x as a constant, it's as if it is a coefficient of this y. So the derivative of x times y is x, and the derivative of y squared is 2y. Then for the partial of f with respect to y at the point 2, 3, we're going to plug in 2 for x and 3 for y. Okay, let's practice finding a few more here. If f of x, y is equal to x squared times y cubed plus x over y plus 4y squared minus 3x. Find the partial of f with respect to x and that partial at negative 1, 7. And then the partial of f with respect to y, and then that partial at 5, 4. I highly recommend that you pause this video and try this on your own. Okay, to find the partial of f with respect to x, we're going to treat y as a constant. So y cubed is just a big constant, it's a big number. X divided by y, that's a number. This y squared is a number. Okay, so if y cubed is a number, it's sort of like the coefficient of x squared then. So for its derivative, the coefficient stays out front, and then the derivative of x squared is 2x. Now for the derivative of x over y, you could use the quotient rule, but that would be the hard way. If y is a constant, I'm going to think of the term x over y as 1 over y times x. I'm just pulling that denominator out front because 1 over y then is a constant, and that is then the coefficient of this x. So the derivative of x over y with respect to x is just that coefficient, 1 over y. Then y is a constant, so 4y squared is a constant, so the derivative of that term is 0. And the derivative of minus 3x is minus 3. Okay, then you can plug in a point if you want. Negative 1, 7 means 7 for y. Negative 1 for x. It's typical, though, to put things in order. So I'm going to write this as 2xy cubed plus 1 over y minus 3 first. Now I'll plug in negative 1 for x and 7 for y. Okay, whatever that number comes to, okay, it doesn't matter. That's the partial of f with respect to x at the point negative 1, 7. For the partial of f with respect to y, we treat x as if it is a constant or a number now. So then x squared is the coefficient of y cubed. So for the derivative of the first term, it's x squared times the derivative of y cubed is 3y squared. Let's see, now we're treating x as if it is the coefficient. So for this term, now I want to think of x over y as, let's see, x is the coefficient. So let's pull that out front and write it as x times 1 over y. But it's hard to differentiate 1 over y. So let's write that as x times y to the minus 1. So for this term, treating x as the coefficient of y to the minus 1, so that derivative becomes x times the derivative of y to the minus 1 is negative y to the minus 2 by the power rule. And the derivative of 4y squared is 8y. And the derivative of negative 3x is 0. And then we can plug in the point 5, 4, 5 for x, and 4 for y. Could clean that up a little bit, but the point is that you compute that out and you get a number. Now when it comes to second derivatives, it's a little bit there's a little bit more to it with partial derivatives, okay? Because there's more options with which variable you're differentiating with respect to. Okay, so there's just like with first derivatives, except we have more than one choice of variables here. So with the first derivative, if f of x equals, say, 2x squared, then the second derivative is the derivative of the first derivative, right? The first derivative would be 12x to the fifth. So the second derivative is the derivative of that, or 60x to the fourth. But when you take the second derivative, okay, so we start with f of x, y, and we have two choices. We can take the derivative of that with respect to x. And I'm going to write it with both notations here. Or we can take the partial of f with respect to y. Okay, now after you differentiate with respect to both x and y, you have a choice of what to differentiate with respect to next. Okay, so if you choose to differentiate with respect to x again, then you've got the partial of f, second partial of f, with respect to x with respect to x, okay? Or you can write it as fxx. Okay, or you could differentiate with respect to y twice, and you would get the partial, second partial of f with respect to y with respect to y, or fyy. Okay, what if though first you differentiate with respect to x, and then you differentiate that with respect to y? Okay, in the xy notation you write them in order that you go from left to right. So you would write f subscript xy. If you're using this notation, it's backwards. First you differentiate with respect to x, then you differentiate with respect to y. Okay, or you could do the opposite. First differentiate with respect to y, and then differentiate that derivative now with respect to x. So first y, then x, or fyx. Okay, either way. Interestingly, if you do it all correctly, these two derivatives will be the same every time. They're always going to come out to the same answer. So it doesn't actually matter which order you go in. Okay, let's practice finding all of these partials. We'll use the simpler subscript notation for these. For f of xy is equal to x squared times y cubed plus x times e to the y. So we're going to start by finding fx and fy. So fx, that's the partial with respect to x. For that, we're going to treat y as a constant. Therefore, y cubed is a constant. So we can treat y cubed as if it is the coefficient of x squared. So the y cubed is the coefficient hanging out front, and the derivative of x squared is 2x. Then for the derivative of x times e to the y, if we're treating y as a constant, then e to the y is also a constant. So e to the y is the coefficient of that x. And let's clean it up. Let's write it as 2xy cubed plus e to the y. That's my partial of f with respect to x. Over here, let's find the partial of f with respect to y. So now we're going to treat x squared as a constant. So x squared is the coefficient of y cubed, whose derivative is 3y squared. And let's see, x is the coefficient of e to the y, so the x stays out front, and the derivative of e to the y is itself. Cleaning this up, we get 3x squared y squared plus x times e to the y. And now we have 4 partial derivatives that we can compute. First, let's find fxx. So I'm differentiating this derivative with respect to x. So we're going to treat this y cubed as if it is a constant. So the y cubed is a constant times the 2 is also a constant. It's also a coefficient of x. So the 2y cubed is a big coefficient of that x. So the derivative of the first term is 2y cubed. And then if we're treating y as a constant, then e to the y is a constant. So the derivative of that term is 0. Okay. Then let's find fxy. So now I'm going to differentiate that one with respect to y. So I'll treat the x as a constant. Therefore, 2x is the coefficient of y cubed. So we get 2x times 3y squared. And let's see, the derivative of e to the y, treating y as the variable, is itself e to the y. So that one simplifies to 6xy squared plus e to the y. All right. Next, let's differentiate. Let's find fyy. Let's find the derivative of fy with respect to y. So I'm going to find the second partial with respect to y. So we're going to treat the 3x squared as the coefficient of that y squared. So its derivative is 3x squared times the derivative of y squared is 2y. And then, let's see, we're treating x as a constant. So it's still the coefficient of this e to the y. So we have the same thing, plus x times e to the y. Okay, and lastly, let's come differentiate fy with respect to x. Okay, so now I'm going to treat y as the constant. Therefore, y squared is the constant. So 3y squared is like the coefficient of the x squared here. So its derivative is 3y squared times the derivative of x squared is 2x. Let's see, and we're treating y as the constant. So e to the y is now like the coefficient of that x. So its derivative with respect to x is e to the y. And if you look at this, we do in fact get the same thing for fxy and fyx. Those are the same.